give us a seminar. Now, Chris is really a true theorist. He is not bound by time or space. In fact, he actually had bought a ticket to come here for next month, and has still managed to arrive somehow. His great freedom from time and space. This has also enabled him to demonstrate crucial skills for being a faculty member, like making a talk on an airplane flight on the way over here. So we're extremely happy to have him here. I hope it's okay. I hope I didn't throw you off your game. I think you're okay.
I'm so off my game now.
Okay. Anyway, Chris Beem. Chris Beem has worked on. He started life as a string theorist. He's worked on the ADS-CFT correspondence, but most recently, I think it's right to say that he is working on supersymmetric quantum field theories, and that's what he'll tell us about.
Right. So thanks, Marcus. Thanks, everyone, for having me and for coming. The title of my talk is Studying Challenging Theories with the Superconformal Bootstrap. The superconformal bootstrap is a phrase that will hopefully become apparent what it means over the course of the talk, but it refers to, roughly speaking, the content of a collection of papers that I've been writing for the past couple of years with various proper subsets of these collaborators. But I want to begin by getting around to explaining what I really mean by challenging theories, and in particular, what I mean is challenging quantum field theories. So I'm going to start off by just saying some general words about quantum field theory. So it almost goes without saying that quantum field theory is a ubiquitous part of modern theoretical physics, and increasingly also mathematics. So of course, quantum field theory is the native language for particle physics, and also it's extremely useful for studying condensed matter physics and things like quantum critical points in condensed matter systems, as well as for areas of geometry and topology and mathematics, and in particular knot theory, which is what's supposed to be illustrated by this picture here. But a point that I think is worth emphasizing is that quantum field theory as a subject is really not something that you could call a technology, and this is a term that I learned from some of my applied math friends. It means that it's not the case that if you have some situation where you think you're supposed to be doing quantum field theory, you're necessarily going to be able to take this thing down off the shelf and turn a crank and get the kinds of answers you're interested in. And at one level, that's true as a technical problem. So quantum field theory is hard, and understanding things like confinement and QCD is hard, even though we sort of think we know what QCD is all about. But I don't mean this in the technical sense. I really mean that there are some hints that we're missing some significant part of the way that we should be thinking about quantum field theory when we use sort of the standard canonical picture of what quantum field theory is about. So this is a slide about the standard canonical picture of quantum field theory, and sort of clearly from the name, it's some kind of theory of quantum fields. And normally, if I want to describe a quantum field theory, what I start out with is some collection of local degrees of freedom, which are some fields valued in spacetime, which give me some, might be some scalars or Fermions or gauge fields or something more exotic. And then with those degrees of freedom, I write down a local Lagrangian that tends to look something like this. And the Lagrangian will be subject to some technical conditions that I'm not going to say anything about, but they need to be there in order for us to think the theory makes sense quantum mechanically. And then, once I have these ingredients, then in principle I want to do something like compute a path integral, which means I write down these symbols that say that I want to integrate over the space of all field configurations weighted by e to the I over h bar times the action. And path integrals, as far as we know, don't really make exact sense mathematically, but we sort of know how to deal with the subtleties. You're supposed to regularize them and learn about renormalization, and these are things that can be tricky, but it's basically an established story. And this is basically a useful paradigm for doing all sorts of things, like computing magnetic moments of the electron to extremely high precision. And there's a disclaimer that goes here that in the rest of the talk, when I say the words quantum field theory, what I mean is Lorentz invariant unitary quantum field theory. And that's not the most general thing that I could talk about, but it's what I care about for now. So, in this standard canonical paradigm, a quantum field theory is basically the same thing as a Lagrangian, subject to these technical conditions that I didn't mention that allow the theory to be UV complete, which is basically the statement that the theory makes sense as a sort of theory in the continuum without having some residual atticization or something of spacetime. Okay, but that sort of pseudo-equation breaks down once I learn about something called duality. And the most basic statement of duality is that there are some quantum field theories that admit multiple Lagrangian descriptions. So this is a picture of duality anticipated by M.C. Escher in the animal kingdom. So if I imagine starting at the top of this picture and having some theory where I basically know what the elementary degrees of freedom are, there's some weakly coupled geese, and then I start turning on a coupling, which moves me down in this picture, the geese become less and less recognizable as the degrees of freedom become more and more strongly interacting. And I might think that by the time I get to very strong coupling, I'm basically going to be talking about some just muck. But occasionally it turns out that when I get to very, very strong coupling, there's some new objects which look like weakly coupled degrees of freedom. In this case, some sort of catfish. And that's a sort of silly cartoon, but this actually happens in honest-to-God interesting quantum field theories. A canonical example is electric-magnetic duality in the maximally supersymmetric version of Yang-Mills theory in 4 dimensions, where there's a strong weak duality like this, where if you turn the coupling on to very high values, then you recover the weakly coupled theory. But there's many, many examples of this. It's essentially everywhere you look once you start looking at supersymmetric quantum field theories, at least. And this idea of duality connects to a lot of deep mathematics. And just to throw out some slogans for people who know the words, mirror symmetry in 2 dimensions is a famous kind of duality that relates different kinds of nonlinear sigma models. And there's connections between this example of duality in 4 dimensions and something called the geometric line length program, which is a deep subject in representation theory. So maybe we need to just relax a little bit and not try to make quantum field theories be the same as Lagrangians, but they're sort of the same as Lagrangians up to some notion of this equivalence relation that I get from duality. And if you want, you might think that having a Lagrangian description is sort of like putting coordinate charts on a manifold, where you can't necessarily cover the entire manifold with one set of coordinates, but if you pass them together, then in any given one, you can sort of think of things in terms of weakly coupled objects. But that is really, that's really hoping for too much, because something that we know, for some complicated reasons, is that there are actually quantum field theories that have no Lagrangian description. So you have something which is essentially unrecognizable from the point of view of our connection with the animals. This is called a blobfish. It's a real thing. It lives off of the coast of Australia and New Zealand. Wow. And you should think that it's incredibly unrecognizable, and if you saw it, you wouldn't even be sure that it was a real animal.
What happens if it saw you?
Run. So these are fairly mysterious objects, and in order to say with confidence that they exist, we usually have to deduce their existence through some indirect arguments, where we start out with some even more complicated system like string theory or M theory, and then in some limit we say that all of the degrees of freedom that don't correspond to some local field theory degrees of freedom decouple. But nevertheless, there's now a lot of very strong arguments that these sort of blobfish objects are really out there, and we should try to understand them. And to understand them is a serious conceptual challenge, because they don't fit into any of the systematic paradigms for thinking about quantum field theory. So this thing is what I mean by a challenging quantum field theory. So in the rest of the talk, what I'm going to describe is what I would term a conservative approach to understanding a particularly interesting class of these weird non-Lagrangian field theories using essentially algebraic methods that are associated with the phrase conformal bootstrap. So, to start, what are the theories I'm interested in? There are things that go by the name of the 2-0 theory in 6 dimensions. There's actually many of them, but people sometimes drop the plural and just say the phrase 2-0 theory as if it's unique. And these have been around. We've known that these were things existing in sort of the animal kingdom of quantum field theory since work of Nadi Seiberg in 1996. And just from the name, it's clear that there's going to be something funny about these things, because it's a general fact that you can't write down interacting continuum Lagrangian quantum field theories in more than 4 dimensions. And I'm told that there was a very long period of time when there was general lore that people believed that this meant that there were no quantum field theories in more than 4 dimensions. But this is not right. It just means there's no Lagrangian quantum field theories. So these 6-dimensional theories do exist, and they come about by this kind of indirect argument that I mentioned before. So if I start my life in 11-dimensional M theory, which is a mysterious subject, then there are some extended objects that are 6-dimensional that are called M5 grains. So the numbering is a little funny, but they're 6-dimensional. And the claim is that if I look at the low energy dynamics of these extended objects, then it's described by some local quantum field theory, and that's what these 2 zero theories are. And the multiplicity in the collection of 2 zero theories that exist has to do with the fact that I can take n of these M5 grains and stack them on top of each other. And for any value of n, I'll get some different theory. So that's a picture which comes from referring to a sort of mysterious subject, which is called M theory. We can say a little bit about these theories just from that picture. We can say important things like what are the symmetries of the theory. They're highly symmetric. So to start with, I'm going to expect them to be some 6-dimensional Lorentz invariant theories. So SO5-1 Lorentz symmetry. That's enhanced to conformal symmetry.
Mean? I mean, you don't have a Lagrangian. Do you not have an action? I mean,
there's no action. There's no fields. There's a complicated indirect argument that there's some system of local degrees of freedom that we don't know how to describe, and we think that it should make sense within whatever is the proper framework for talking about quantum field theory. These are very mysterious. I don't mean to imply. I mean,
how do you calculate anything observable?
That's the subject of the talk.
Okay.
Can
So-
you say something more about the first sentence, interacting continuum greater than 4 dimensions? What does that mean?
Yeah. So once you take including the technicalities associated with regularization and renormalization and everything, what a continuum Lagrangian quantum field theory amounts to is starting out with a free field theory and then turning on interactions which are relevant in the renormalization group sense. And what you can see by a simple exercise is that in more than 4 dimensions, if you start out with a non-interacting set of free fields, then any interaction that you can turn on is irrelevant in the renormalization group sense. So you can't make sense of this as a continuum construction. So I referred to a technical condition, which is this relevant versus irrelevant in the renormalization group sense. But it means that if you try to make sense of it at short distances after you do the deformation, it doesn't make sense.
Could you give some specific references for this claim?
Well, you can read references to the claim, at least in this paper from 1996 by Seiberg. But the actual exercise is very, very fast. If you just because free field theories are really easy, so you can just write down a free quadratic Lagrangian for scalars and fermions, and then you can read off what the scaling dimensions of the fields are, and then you can try to write down any interaction terms that make sense, and just dimensional analysis tells you that
Does that
it's
mean
irrelevant.
that if I'm in higher than 4 dimension, then and I write down such a theory where all these interactions are irrelevant, that you will not get any scattering of particles or whatever?
So you can do effective field theory, which means that you try to make sense of the theory after you've added the interactions as a theory with a cutoff, and then you only refer to low energy observables up to some higher order corrections that you don't know how to compute. But what I really mean here, so an effective field theory is not the same thing as a continuum field theory because you can't take the cutoff to infinity and have it make sense. So you can compute low energy physics. There are actually systems, even in more than 6 dimensions, that have a low energy effective field theory description, but do not have a UV continuum quantum field theory description. So these objects are special. Are symmetric and special in a couple of ways. First of all, they're conformally invariant, which means that they're fixed points of the renormalization group flow. These theories have no intrinsic scale. So that enhances the Lorentz symmetry in 6 dimensions to the conformal group in 6 dimensions. And they're also maximally supersymmetric, so they have a lot of fermionic symmetry generators, which enhances this SO62 to some supergroup of symmetries called OSP 8/4. And of course, saying what supersymmetry is once I don't have a Lagrangian is a little bit indirect, but whatever observables I have in the theory have to fit into sort of representations of this supergroup. And I should mention that there's one place where you can make perfect sense of all the correlation functions or whatever you want in this theory, which is in the limit where this number n goes to infinity. And in that case, there's actually a holographic description in terms of 11-dimensional supergravity in 7-dimensional hyperbolic space times the force sphere. This just means that there's some classical supergravity calculations that you can do in 11 dimensions, which will produce for you a collection of correlation functions that look like 6-dimensional CFT correlation functions.
Can you remind me what the number n represents?
It's the number of these brains that I used in order to deduce the existence of this theory. Yeah. Joe.
So you said a minute ago that you couldn't identify any fields, but just by saying correlation functions, you've got fields of which you're calculating the correlation functions.
Well, I'm inclined to draw a distinction between the word field and the word operator. You might want to conflate them. So these theories have some.
Conflate them,
So then they have fields, but they're not weakly coupled fields. So I don't know how to formulate this kind of path integral picture where the field is a thing that gets integrated over in some Lagrangian.
That's just perturbation theory. You're saying you can't do perturbation theory. How about that?
I can't do perturbation theory, but I can't even, it's not just being able to do perturbation theory, because even in QCD, right, if I have some low energy phenomenon that's strongly coupled, the continuum of the theory makes sense as a continuum theory because the microscopic degrees of freedom are weakly interacting fields. Because in the UV, I have asymptotic freedom, and in the UV I just have sort of these things that look like reasonably classical fields.
Still you assume the existence of a P.
That's right. So I'm going to get to sort of using the CFT approach momentarily. There are some local measurements, quote unquote measurements, that I can make in these theories. So there's some collection of operators that I can insert at points. I don't necessarily know what they all are. I don't know the spectrum of operators in the theory, but there should be some operators. And they should have correlation functions that obey the rules of quantum mechanics and symmetry and everything. I totally agree. I haven't told you what this theory is because we don't know the definition of this theory. What I'm going to get around to is saying sort of a minimal version of what I might mean by this theory, and then trying to get something out of that minimal version. So, in this large N description, you have some way of computing things, but I want to emphasize that you're really stuck at the n to infinity limit because there's no way of computing 1 over n corrections. Often in ADS-CFT, you find a large N description of a theory, and then there's some systematic machine that we know about for computing the 1 over n corrections. But here the 1 over n corrections amount to some quantum gravity corrections in M theory, which is a subject about which we know very little. So, before getting into how I'm going to actually do anything with these theories, I want to point out that even though this has all been incredibly vague, and I don't actually know how to define these theories, they still seem to be important in a few senses. So one has to do with just their placement within the space of algebraic structures. So Werner Nahm, in 1978, classified all the possible ways that you could have a supersymmetric extension of conformal symmetry. And it turns out that in more than 6 dimensions, you can't have it. So you cannot have a conformally invariant quantum field theory that has supersymmetry in more than 6 dimensions. And these are things that have conformal invariance and supersymmetry in 6 dimensions. So in some sense, they're sort of realizing this top of the pantheon of possible superconformal symmetries. And that's a speculation that I don't want to talk about, but you can ask me about it afterwards. There's also a reason that these theories are interesting just from the indirect argument I used at the beginning. Somehow these theories are the theory of M5 brains, which are some fundamental objects in a mysterious theory called M theory that's very confusing. And so it would be nice to be able to say more about these. And finally, this six-dimensional thing, people have been able to argue using various clever arguments that, again, to argue anything with these things, you need to sort of never really think you know what the theory is. Just imagine that it exists and it obeys some basic rules. But starting with this six-dimensional theory, you can sort of populate a lot of the landscape of lower-dimensional supersymmetric quantum field theories that we know about by considering the case when instead of having the theory in flat six-dimensional space, you have it in some lower-dimensional space, like four flat dimensions times a compact Riemann surface or something. And then at long distances, this will look like some sort of four-dimensional quantum field theory. And you can get a lot of interesting quantum field theories that way. And in fact, in some sense, this picture of getting lower dimensional theories in terms of this fundamental six-dimensional object explains duality in many cases, where explain should really be in quotation marks since I'm using a mysterious object to do the explaining. And this is the basic example, which goes back to work of Witten in 1995. So if I consider the case where my six-dimensional theory is placed in four flat dimensions, or four infinite flat dimensions, times a 2 torus, then one can argue that at long distances it will look like the n equals 4, the maximally supersymmetric Yang-Mills theory in 4 dimensions with gauge group SUN, where the n matches the number n that I had before. And the modular parameter of the torus, so here's a torus, and the modular parameter is just this, this complex number tau that gives me the shape of it. The modular parameter of the torus gets identified with the complexified gauge coupling of the Yang-Mills theory. And then it's just a standard fact that toruses with modular parameter tau have different values of tau correspond to the same torus. So there's some modular transformation. If I replace tau with some tau prime that looks like a tau plus b over c tau plus d, where a, b, c, d integers are obeying this condition, then I actually get the same torus. And applying that transformation to the complexified gauge coupling gives me the action of S-duality in super Yang. So, these are some reasons to worry about this confusing theory, or these confusing theories. But if I want to say more, if I want to actually be able to compute something, or even say what it would be to compute something, I need to decide what I think the theory is at some basic level, just to set up the framework. And depending on my political persuasions, I might have different opinions about what this theory should be. So a rather liberal interpretation of what this theory is just uses everything I've said about where it comes from. So it's the theory of M5 grains. And that includes anything that I might, so having that description puts in my toolkit anything that I might think I know about M theory and everything. But it also involves conjuring into existence another mysterious theory, and is not necessarily obviously helpful because I don't have many systematic tools for doing M theory. A much more conservative approach is just to say that if this theory exists, then there should be some list of operators, which are the things that participate in having correlation functions. And those operators should be consistent with superconformal symmetry and whatever the rules are of quantum mechanics that govern local correlation functions of operators in quantum field theory. And I'm pretty sympathetic to this conservative point of view. In a perfect world, I would spend all my time using this conservative version to try to understand these theories. But it helps to be a little bit moderate and cross the aisle, and use, when necessary, some basic facts that can be extracted from this liberal point of view to sort of supplement this more conservative operatorial picture.
So is there a parallel version? Sorry, is there a parallel version of your talk when you change 5 to 2?
There is a story when you change 5 to 2. Sorry, you mean in that 5?
That 5, I think it's the only 5. Yeah.
Yeah, you could definitely try to say a similar story, except that there's a sense in which the theory of M2 grains as a quantum field theory is much less mysterious than the theory of M5 grains, because we actually know how to give a UV path integral description, which is supposed to, as its low energy limit, be described by that M2 grain theory. So it's not as fundamentally challenging in the same way.
Do you think that this theory is defined on any six-dimensional manifold?
So yes, with caveats.
Okay.
So I'll be happy to talk about it later. There's some technicalities, but more or less, yes, is the answer. Yeah, Joe.
Is there anything short to say about how you conclude that the theory, which is coming from M theory and then 5 grains, is going to be a theory in flat space-time, Lorentz invariant, as opposed to some kind of quantum gravity?
The limit in which the description is supposed to be a field theory is in the extreme low energy limit of this M theory construction. And in that limit, gravity becomes infinitely weakly coupled at infinitely low energies. And so the gravitational degrees of freedom in the M theory construction decouple. So this is why this is not a theory of gravity. Because there is a theory of gravity that includes these things, but I'm looking at a decoupling
Imply
limit.
that it was UV complete, and then you'd just be reversing that limit.
Well, it's UV complete because it's conformally invariant. So there's some nested picture, right? So I can start out with M theory, which is something, and then there's a low energy limit of that. So that's a UV completion of something that involves these two zero theories. But then these two zero theories are in some sense an IR fixed point of that construction. And but then they are purely field theoretic. So by taking that IR limit, I've extracted something which is purely field theoretic when I started out with something that was quantum gravity. And then that field theoretic thing can be sort of a new UV fixed point for purely quantum field theory. So, I want to adopt this conservative approach, which is roughly the approach that gets labeled the conformal bootstrap, or the approach that's amenable to doing something called the conformal bootstrap. And essentially all I have at my disposal in this conservative approach is the idea that there are correlation functions of local operators and the constraints of symmetry. So the first part of the symmetry that I want to deal with is conformal symmetry. Conformal symmetry is very powerful. The most obvious thing that it does is that whatever these things called operators in this theory are, they have to organize into representations of that conformal symmetry. And this gives me things that people call conformal families, which is just a fancy name for a representation. And the conformal families are labeled by some scaling dimension, because scaling is an element of the conformal group, and some Lorentz spins. And then I have the operator itself, which is this operator, which is usually called a primary, and then the so-called descendants, which are just derivatives acting on the operator. So I have some collection of O delta L's, and then all of their derivatives. Those are things I should be able to take correlation functions of. But the real power of conformal symmetry is that there's a convergent OPE, which allows me to start thinking about these theories algebraically. So the existence of a convergent OPE means that if I take a couple of these operators and I put them down, and I can draw a sphere around them that separates them from anything else I might have inserted elsewhere, then I can replace those two operators with a sum of individual operators with some coefficients which are fixed entirely in terms of conformal symmetry up to a single numerical coefficient, which is encoded in the 3-point functions of the operators. So if I know the 3-point function of OI, OJ, and OK, which essentially amounts to knowing a single real number, then I know what this coefficient function is.
So if you have a manifold of space, and x minus y doesn't make any sense.
This is in flat space. I totally agree. But I'm trying to study a theory that I don't understand at all. I might as well start out just doing the local story in flat space. And then, once I have this algebraic structure that allows me to replace pairs of operators with individual operators, this allows me to compute an arbitrary correlation function of any number of operators in terms of just these 3-point functions in the spectrum. The combination of all the 3-point functions and the list of operators is sometimes called the CFT data of the theory. And just using that data, I can in principle compute any correlation function, because if I start out with n operators scattered around, I can just start pairing them up with their nearest neighbors and keep pairing until there's nothing left. And everything is expressed in terms of these OPE coefficient functions. But if I were to give you just a random list of operator dimensions and spins and a random collection of 3-point functions, that would not be a conformal field theory because the CFT data is constrained by this thing called crossing symmetry. And this is a demonstration in the case of 4-point functions what crossing symmetry is. You can see if I put 4 operators down, then there are inequivalent ways that I can pair them up. And this will give me inequivalent expressions for what the 4-point function is in terms of this CFT data. And I end up with an expression that looks like this, where these G delta L's are some functions called conformal blocks that are determined by conformal symmetry just in terms of the scaling dimension and the spin. And the fact that these two expressions for the same 4-point function give me the same function is non-trivial. That's a constraint on the CFT data. And there's one equation like this for every possible 4-point function I could write down. So for every quadruple of operators that are in my spectrum, I get a function like this. And the idea of the conformal bootstrap, which goes back to these various gentlemen in the early to mid 70s, is that somehow you should be able to stare at these equations and just solve them, or do something useful with them. And that will be essentially, at least for the purposes of correlation functions of local operators, your definition of a theory will be a thing that solves all of these consistency conditions. And something that you should know before you think you're just going to start writing down these equations and solving them is that you necessarily need an infinite number of conformal families. That's actually a consequence of these equations. You can prove relatively quickly that you won't be able to solve even one of those equations unless you have infinitely many conformal families. But that means that there's infinitely many equations in infinitely many unknowns. So you have a proliferation of infinities, and you just are sunk if you're just standing there sitting there staring at these equations saying, how am I going to solve them? You need some way to organize the infinities. And I'm not going to talk about 2 dimensions anymore in this talk after this comment, but it should be noted that famously, in 2 dimensions, the conformal algebra is actually infinite dimensional instead of finite dimensional, and that does this organization of infinities for you and allows you to make progress on this conformal bootstrap problem in 2 dimensions. And so there's many solved theories in 2 dimensions coming from this approach, but that's very special to 2 dimensions. In 3 or more dimensions, I think it's fair to say that there was no significant progress on getting something useful out of these equations until some work of Vertazzi, Richkov, Tony, and Vicky in 2008, who adopted a certain sort of inspired numerical approach to trying to get some useful information out of these constraints. And since that work in 2008, there's been a whole lot of really beautiful additions to this idea, and there's a lot of bells and whistles added onto the basic setup that they had. And I don't have time to go into it, but I want to give just sort of a rough sketch of what the idea is that allows you to get some useful information out of these equations. So part 1 is you rewrite that equation I had on the previous slide as a sum rule. So admission, this equation is not an actual rewriting of the equation on the previous slide, because in all of these equations I'm dropping factors and leaving out details that make them uglier. But you rewrite the true version of the equation, and you get a sum over the operators that are in your spectrum, of some 3-point functions squared, times a combination of the conformal blocks. So you've taken the right-hand side of the previous equation and moved it to the left-hand side. So it's the crossed version where the conformal cross ratios u and v have been replaced by v and u. And that thing is supposed to be equal to 1. So this is an equation that tells you that some positive, so these coefficient squareds are some positive real numbers, some positive linear combination of this set of functions, which are just fixed by conformal symmetry, has to be able to reconstruct the function 1. And then the idea is that you can start making assumptions about the spectrum of your theory. And an assumption about the spectrum of your theory limits the set of these functions that you have available to you with which to reconstruct the function 1. And it might be the case that if you limit yourself too much, you'll be able to prove that there's actually no way to reconstruct 1. So here's a stupid way that could happen. If if you restrict your spectrum so much that you can then prove that all of the leftover functions that you have available have second derivative greater than 0 at some point, then there's no way you can add together a positive linear combination of them and get 1, because the second derivative of 1 is 0, and the second derivative on the left-hand side would be a sum of positive numbers. And that's a very basic version, and then there's an extremely souped-up version of this, which is much more powerful, which morally is looking for a much better condition than this sort of second derivative greater than 0 condition. And the key word for that is convex optimization. That's the relevant sort of applied math technology that goes into doing this. And just to show what kind of situation presents itself once you start doing these numerical analyses, this is a plot from some work of Chiral, Schauk, and Miguel Palos in 2012. And what's going on in this plot is that every point in this plot represents an assumption about the spectrum of a theory. So the x-axis corresponds to the dimension of the lightest scalar operator, and the y-axis corresponds to the dimension of the second lightest scalar operator. So that's some assumption about the spectrum that limits the functions that you have to use to try to solve this sum rule. And in some regions, you can exclude that assumption by proving this kind of impossibility of the sum rule. In some regions, you can't exclude it. And then there's some interesting boundary region. And there's two very interesting facts about the boundary region to know. One is that if there happens to be a theory that corresponds to the assumption that puts you on the boundary, so if there's a theory that has the value of these two scalar dimensions, which puts you at some point on the boundary, then as a part of this numerical machine, you can systematically reconstruct the CFT data in that theory. And the second interesting thing is that there appear to be actual theories that do live on these kinds of boundaries. So this is an example from 2 dimensions where you didn't really need to do numerics because we have lots of exact solutions. But it turns out that if you plot those exact solutions, these are the two-dimensional interval models. If you plot those on this kind of an exclusion plot, then they appear on the boundary. So this is a sort of miraculous thing. I think it's fair to say that generally it remains poorly understood what one should really think about the property of a theory that allows it to be analyzed in this way. So a theory that lives on this kind of an exclusion threshold is numerically accessible by these numerical methods. You can, in principle, start reconstructing lots of CFT data. And the thing that makes a theory numerically accessible is mysterious. If you hand me your favorite conformal field theory, I won't be able to tell you whether or not it will have this property or not. But if it does, then you're in great luck. So that was all a story about conformal invariance. I'm interested in these weird 6-dimensional theories that are not only conformally invariant, but superconformally invariant. So there's a lot more symmetry. The most basic thing, which is true when I have supersymmetry instead of conformal symmetry, is that instead of just having operators and their descendants, I have operators, their superpartners in their descendants. I have some fermionic symmetry generators that transform one operator into an operator of opposite fermion number. This is sort of what supersymmetry means in the context of a theory where I don't have a Lagrangian, I just have operators. Now, an interesting thing that happens in supersymmetric theories is that there are lots of interesting kinds of operators that live in non-trivial representations of the superconformal algebra. So in particular, generally I can act with up to some maximum number of supercharges on a primary operator and get more operators. So in the case of these 2 zero theories, there are 16 supercharges, so I can act with 16 Qs. But there may be some special operators that have the property that if I act with some smaller number of Qs, if I sort of act with less than the maximum number of supersymmetry transformations, I'll actually get 0. So they're invariant under some of the supersymmetries. And roughly speaking, that is what we call a BPS operator. And a sort of belief that comes from all the intuition that we've gained from studying theories with Lagrangians that we understand fairly well, is that in supersymmetric theories, you generally will have infinitely many of these kinds of operators. So I don't actually have a proof of that, but it's generally expected to be true. And this should be contrasted with the case of an ordinary conformal field theory. In a conformal field theory without supersymmetry, there's basically one way for an operator to be special from the point of view of its transformations under the symmetry algebra, and that's for it to be a conserved current, in which case some action of the derivative acting on your operator gives 0. And we know that conserved currents have to do with global symmetries, and I usually only have finitely many of those in a theory. So a difference of theories with a lot of supersymmetry is that there's a much bigger sort of playground of nice, special, symmetry-protected operators that I have to work with. And now here's a non-trivial fact that I really can't give the details about because it ends up being extremely complicated. But in theories with a lot of supersymmetry, the operator product expansion, the algebra of operators that I get by doing this operator product expansion, actually admits a non-trivial truncation to a sort of subalgebra that only involves these BPS operators. So in quotation marks, I'm saying that there's some kind of operator algebra where multiplying two BPS operators together gives me a sum over other BPS operators. I should have had the disclaimer first. The disclaimer is that this truncation is very complicated. So this thing in quotation marks makes it look like to do the truncation, I just throw away all the operators that aren't BPS and just do the ordinary OPE of operators that are BPS. But that is not the case. You need to do a bunch of contrived things. But you can do them. You get this truncated algebra, and generally this sort of truncated BPS algebra is much simpler than the full operator algebra. For example, in these 6-dimensional theories, just using the structure of superconformal symmetry, you can show that in this truncation, the operators that participate are required to lie on a certain plane inside of your flat 6-dimensional space. And then in that plane, they have an algebra which is meromorphic. So there's some coordinates z, z bar, w, and w bar in the plane. But in the OPE of two of these operators, the only things that appear are z's and w's, not z bars and w bars. So this kind of a meromorphic operator algebra has a name. It's called a chiral algebra. It's also sometimes called a vertex algebra or a vertex operator algebra, depending on who you ask. It's a well-studied thing in mathematics, and it appears in 2-dimensional conformal field theory.
Is it general that they reduce to these 2-dimensional subspaces, or is that just for this particular theory?
It's true for a couple of cases that I'll mention at the end of the talk. There are more cases, but it is not always the case. But it's true. So what I mean by these theories is any 6-dimensional theory with the maximal superconformal algebra as its symmetry. So this fact follows from just the presence of the maximal superconformal symmetry. And what's nice is that crossing symmetry, so this is still some operator algebra that allows me to replace pairs of operators with sums over operators. So it's still the case that I can compute correlation functions of many operators in many different ways, and that there's some crossing symmetry condition. And it's still non-trivial, but it's now much more tractable. And the relevant mathematical analogy is that it's as much nicer than the general case as complex analysis is to real analysis. That's really exactly what I mean, because now we have meromorphic functions involved. So we're really doing complex analysis when we analyze these algebras. Now, in the 2-0 theories, this is where I'm going to become more of a political moderate than a political conservative. We know a little bit about the spectrum of BPS operators in these theories through various complicated indirect arguments that come from the M-theory construction. And it turns out that given what I know about the BPS spectrum, it's actually possible to solve the crossing symmetry condition. So it's possible to solve the bootstrap for this truncated algebra completely. And the answer is a thing that has a name. So that should tell you that it's something that can be understood. The meromorphic operator algebra that you get is something called a WN algebra, where that n is the same number that appeared as the n before.
Do you have a uniqueness statement, or just existence?
Yeah, this is a uniqueness statement. This is the unique answer. And this means that you can actually calculate things, because these WN algebras are totally tractable. I mean, there's a systematic way to compute arbitrary correlation functions in the WN algebra. And now we know a dictionary that allows us to relate those things to certain correlation functions of BPS operators in the 2-0 theory. So this is some sort of a triumph. We've basically used symmetry, along with a little bit of information that came from sort of the origins of these theories in M-theory, in order to be able to actually compute correlation functions. And something that you can then go and do is take the one case where we know what we're supposed to compare to, which is when this number n goes to infinity. So then this Wn algebra becomes something like a W infinity algebra. And you can compare the kinds of three-point functions that you get algebraically just by solving crossing symmetry to the calculations that people were able to do in 11-dimensional supergravity. And you get some non-trivial looking junk, but it's the same non-trivial looking junk. So depending on your perspective, this is either a check of our approach or a check of the ADS-CFT correspondence.
Is there any connection between this appearance of Wn and the Wn's appearing in three-dimensional high-speed theories?
I would love to know the answer. I think the answer is maybe yes, but all of my ideas are extremely wishy-washy.
Does it mean that you have some hidden Wn symmetry in your business?
It's not really, it depends on what you mean by that. So you don't expect this W symmetry to sort of infiltrate the non-BPS part of the theory in a direct way. So you can't turn around, for example, in two-dimensional CFT, you would say, oh, I have a theory with W symmetry, and then the rest of the theory has to sort of be organized in representations of that W symmetry. That's not the case here. It's not the case that this W symmetry somehow controls, in an obvious way, the non-BPS spectrum in correlation functions. But it has something to do with it. So the answer to your question is not in a simple way, but maybe, hopefully, in some more complicated sense. So something that we haven't done, but which can actually be done systematically, given this observation, is that you can start computing the finite n corrections to this answer. From our point of view, this is just some W algebra problem that, in principle, could have been done back in the 80s or 90s. But what the answer now means is something telling you about quantum gravity corrections to M theory in 11 dimensions, which makes it sound like a more exciting project. So that's all an analytical story, and it's very beautiful, I think. There's a lot of interesting structure hidden in these superconformal operator algebras that we're talking about. But we can try to do more. I've been making this specialization to the BPS operators, but in principle, I'd like to be able to say something about the general spectrum of the theory and general correlation functions. And so you end up with a little flowchart. This chiral algebra story actually plays an essential first step in trying to set up this more complicated numerical program I outlined before. So once we have this solution to the crossing symmetry problem for the chiral algebra, you can extract the CFT data for all of the BPS operators in your theory. And then using that, you can set up the crossing symmetry conditions for the rest of your theory in a way that only refers to the CFT data of your non-BPS operators. So you've sort of taken care of all the nice parts of your theory, just solved them. And now when you're going to do numerics, you only have to worry about the less nice stuff. You don't have to somehow numerically bootstrap the nice stuff. And now this is my last slide, and this is work in progress that isn't really finished. But you can play this game, and you can do the kinds of exclusions, numerical exclusion games that I described before, and you can get a plot that looks like this. So here's a plot where each point corresponds to some assumption about the spectrum of non-BPS operators in this mysterious 2-0 theory. The x-axis is the lightest scalar operator, and the y-axis is the second lightest scalar operator. And again, you have lines where regions above the lines are all excluded numerically, and regions below are not excluded. And I think you should really be struck by the fact that the shape of this plot looks just like it did in that two-dimensional case, where there was all sorts of interesting stuff happening along the boundary, and where in particular, this point here corresponded to the 2D Ising model. Now I want to claim that this point here is likely, I don't want to make categorical statements, but you can dig into the numerics a little bit and try to understand what's responsible for this shape in the plot. And there are good reasons to believe that that interesting point really corresponds to the minimal 2-0 theory, where this letter n is equal to 2. And I didn't mention it before, but I should say that the n equals 1 case isn't interesting. The n equals 2 case is the first interesting 2-0 theory. So I can't help but propose a potential slogan that these 2-0 theories could be something like the Ising model of the 21st century, Who knows? Maybe they'll be solvable. So with that, I want to wrap up. Just to summarize where we stand, there's some rich algebraic structure connected with the existence of superconformal symmetry. I talked about this case in 6 dimensions, where 2, 0 superconformal symmetry gives you a structure which is a chiral algebra. It's also the case that in 4-dimensional superconformal field theories, with at least half maximal supersymmetry, there's a similar sort of truncation to an algebra that looks like a chiral algebra. And then some work in progress. In some work in progress, we've shown that in 3-dimensional theories, with again half maximal superconformal symmetry, there's a truncated algebraic structure that has something to do with deformation quantization. This is another interesting tractable algebraic associativity problem. From these rich structures, we can start to compute some exact correlation functions, at least of these BPS operators, in hard-to-understand theories, like the 2-0 theory and also in various non-Lagrangian theories in 4 dimensions. And then you can feed that into this numerical game, and there really seem to be some strong indications that at least the minimal 2-0 theory has this special feature of being numerically accessible. And so to finish, just a couple of words about where things can go in some long-term sense. One thing that we really, that we're starting to do, but I think is going to be a long-term project, is to really explore all of these kinds of protected algebraic structures that follow from supersymmetry combined with conformal symmetry. This is something that could have been done actually a long time ago if people were motivated. It's all the kinds of stuff people were doing in the 90s with supersymmetry, where you can compute all sorts of things exactly. But you really need to believe that conformal symmetry is going to do a lot for you before you think it's worthwhile. There's an obvious question, which is whether these conformal field theories that have this special property that somehow they can be analyzed numerically using these bootstrap tricks have some analytically special features. You can't help but hope. I mean, the Ising model has this property, and it's analytically tractable. So, what about these other theories? And we really don't know the answer. I think it's a wide open question. But the fact that we don't have the answer has to do with the fact that I don't think we really know the right mathematical framework for analyzing the conformal bootstrap. The way this numerical game works, you're really brutally truncating the system of constraints that come from crossing symmetry, and doing remarkably well, given how brutally you've truncated them. But we should really, I think, spend some time thinking about whether there's a clever, less brutal way to start organizing these infinities, given that we now have hope that there's something hidden in there. Thank you.
Questions? So here,
Yeah, Albert.
so here you consider the series, considered series flat space.
Yeah.
What about other manifolds? So then you come to get some results for about computation with other manifolds.
Yeah. So in this very conservative definition of what I mean by the 2-0 theory, I really am not giving myself enough in order to be able to do things like put the theory on a non-trivial manifold and ask what the low energy theory is. I have no idea how to take the list of operators, local operators in my theory, and their 3-point functions, and tell you what is the theory if I compactify this thing on, a Seifert manifold or something. And so I think that's a great question. The fact that it seems like you need to know more to do that kind of thing is a strong suggestion that this bootstrappy approach may not yet exhaust the full correct axioms for quantum field theories. I don't think we know what the full correct axioms are for quantum field theories, so that's not surprising. But using this, you can't do that kind of thing. There's a lot of things you can't do with this approach. But when you're dealing with theories that you don't understand at all, somehow feels like you're best off being the most conservative, at least to start.
So in mathematics, construction of W algebra representations
using for the gauge theory has been understood as a kind of mystery. You're saying that that is probably because we are looking at the truncated DPS. That's one explanation. And then the final remark you made was that something more general should be looked at by mathematicians.
Yeah. So to your first point, you're referring to the AGT correspondence?
Yes.
So I didn't say anything about that, of course. One strongly suspects, based on this reappearance of the W algebras related to the 2-0 theory, that, well, my inclination is to say that at the end of the day, this structure must be the microscopic explanation for why that AGT story makes sense. Mm-hmm. Trying to actually nail that down and explaining how this sort of operator algebra statement turns into that statement about instanton partition functions and things is very hard. I don't know how to do it. I'd love to talk about it. I think it's really interesting to try to make the connection, but we don't know how to do it. To your second question, yes, I absolutely think that this crossing symmetry problem in the full theory, where you're not restricting to BPS stuff, is something which is more or less mathematically well posed. And so I really think that that it is fair for me as a physicist to suggest to a mathematician to look at these equations and know that there should be a lot of content in them, but that we are having trouble figuring out the best way to extract that content.
It might be worth commenting that I think a lot of the progress in the original paper might be due to the fact that Slava Rychkov has a PhD in mathematics and did approach these equations the way I think it's fair to say that a mathematician might approach them, using some basically tools from analysis and so on to generate some useful inequalities out of these equalities. So,
absolutely, I think it's an interesting story that I won't tell in its completeness, but at some level that was the insight for whatever those guys' reasons were. The fact that they stopped just being stumped by the fact that solving these equations was hard, and instead they decided to just try to find inequalities that were true.
Because they tried to rule out
theory. Well, I wasn't going to bring that up. I know that.
Yeah, it's because an inequality is all you need to rule out some crazy guy's theory. Anyway.
Yeah, Jeff.
Steve. Sorry.
It didn't seem like gauge invariance played too much of an issue when you were talking about. So I have two maybe related questions.
Yeah.
That, have something to do with gauge invariance. So suppose I gave you the CFT data for some theory. Could you tell me if it was gauge theory or not?
No.
Okay.
But I'm not sure whether the property of being a gauge theory is well defined. So.
Okay. So then the second question is more specific. So probably NF equals 12. SU3 gauge theory has an infrared stable fixed point. So suppose I gave you the CFT data for that right at the fixed point. Could you tell that it's connected in some way to a ultraviolet stable fixed point?
I couldn't, and I don't. I think that probably at the moment, no one could give you a systematic way to do so. This is, I definitely do not want to suggest that I think that taking this bootstrap approach is literally the end-all of ways to think about quantum field theory. The value is that it's very conservative and that it seems to be able to apply even when you don't know what else you have to work with. So there's all sorts of questions like the ones you're raising about how well you can really understand flows between various fixed points, and the questions that Albert was asking about compactifying on manifolds and ending up with new theories. Certainly don't seem easy and may not even be in principle answerable in any systematic way from this bootstrap point of view. But there are some things that the bootstrap can do, and apparently one of them is start giving us some insight into a theory that we literally do not know how to define in any other way.
Any other questions? Okay, so we're going to have a discussion with Chris tomorrow at what? I forgot.